Welcome to this deep dive. It looks like you're really getting into some fascinating stuff about the nature of light from this physics textbook you've sent over. Wave optics, huh?
Definitely a great area to dive into.
It sure is. Get ready to bend your mind a bit because we're going to unpack how light bends, bounces around, and get this, sometimes seems to just vanish.
It's pretty amazing how scientists over the years have figured out all these mysteries surrounding light.
Totally. So speaking of figuring things out, wasn't there some debate back in the day about whether light is even a wave at all? Didn't Newton have some other idea?
He did. Newton's corpuscular theory saw light as, well, a stream of particles, tiny little particles.
Okay, particles. And that explains some stuff about light.
Oh, absolutely. Like reflection, for example. His
Yeah.
theory explained that quite well. But it really struggled when it came to predicting what happens when light, travels between different materials, like air into water.
So what was the other side of that debate? If Newton thought it was particles, what was the alternative?
In the late 1600s, along comes Christian Huygens. And he proposes this, well, at the time, really revolutionary idea that light is a wave. He imagined it kind of spreading out like ripples you see when you, drop a pebble in a pond.
I can picture that.
Yeah.
So how did scientists settle this debate? I mean, Newton was a pretty big name, right?
Right. But science is all about testing and experimenting. So picture this. You shine light from air into water. Now, Newton's particle theory says the light should speed up in the water, but Huygens's wave theory, it predicted that light would actually slow down.
That's interesting. So what happened?
Well, it might seem counterintuitive, but light really does slow down in a denser medium like water.
Really? So light is slower underwater than in air. Huh. Learn something new every day.
It's true. And it took a while to prove it. It wasn't until 1850 that a physicist named Foucault did an experiment that finally put Newton's particle theory to rest. So, yeah, sometimes even the most famous scientists get things wrong.
So Huygens was right. Light is a wave.
Yeah.
But what's with all this talk about wave fronts and secondary waves?
Let's break down Huygens' principle. Imagine you're looking at the leading edge of a wave. That's the wavefront. Every point on that wavefront is vibrating together. Now, according to Huygens, each of those points acts like a tiny source of new waves, spreading out in all directions. We call these secondary waves or wavelets.
Okay, I think I'm following you. So it's like each point on the wavefront triggers its own little chain reaction.
Exactly. And those secondary wavelets combine to create the next wavefront and so on and so on. That's how the wave propagates.
Okay, that makes sense. But if each point is sending out waves in all directions, wouldn't that mean some light could travel backward?
You're sharp to catch that. It puzzled Huygens, too. He had to assume that these secondary waves were stronger in the forward direction and, well, basically non-existent going backward. Much later, a more refined theory about waves actually confirmed this.
So Huygens' principle isn't just some abstract idea. It actually explains how light behaves, right?
Oh, absolutely. And it helps explain reflection and refraction really well.
Reflection, okay, like bouncing off a mirror, but refraction. I'm not sure how a wave explains light bending when it goes from, say, air into water.
Well, think about it this way. Remember, light slows down in water. Right.
Denser medium, slower speed. Got it.
Okay, good. So when a wavefront hits the water, the part that hits first slows down while the rest of the wavefront is still going its original speed in the air.
But the wavefront gets distorted as it enters the water.
You got it. That's exactly what happens. And that distortion, that's what makes the wavefront bend. That's refraction. And how much it bends depends on the speed difference in the two materials, something we call the index of refraction.
I never thought about it that way. So the light slows down in a denser medium. So does it actually take longer to travel through it?
This is where it gets really interesting. While the speed is lower, the wavelength of the light gets shorter. It all balances out. Light takes the same time to cover a certain distance, regardless of the medium. And this difference in wavelength is actually why we see different colors when light passes through a prism. Each color has a different wavelength and bends a bit differently.
That's how rainbows work.
Ah!
Wow. It's really amazing how much Huygens' principle can explain.
It really is. And it gets even cooler when we look at how lenses work, like the ones in your glasses or a telescope.
Lenses, right. They use refraction to focus light.
Precisely. Think of a lens as this carefully shaped piece of glass that basically manipulates the bending of light.
So like with a convex lens, the light all comes together at that one point called the focal point, right?
Yes. And you can explain that using Huygens' principle. The thicker parts of the lens slow the light down more, and that causes the wavefront to curve inward. That curved wavefront then converges to a point, and boom, you get the focal point.
So it's like the lens is shaping the wavefront to focus the light.
You got it. And here's a cool detail from the textbook. The light actually takes the same amount of time to reach the focus, whether it goes through the center of the lens or near the edge. It's kind of like the lens compensates for the longer path by slowing the light down more in the thicker parts.
Wow, that's mind-blowing. Like the light knows exactly where to go and how to get there at the same time. What other amazing things can this principle explain?
Well, let's talk about interference next.
Interference. Isn't that like when waves crash into each other? Like when you throw two rocks in a pond and the ripples intersect?
That's a great example. Interference happens when two or more waves, well, overlap, and their amplitudes can either add up, making a bigger wave, or they can cancel each other out. It creates these, well, really fascinating patterns.
So when waves add up, they get bigger, and when they cancel, they kind of disappear. What's that look like with light?
Think about those bright and dark bands you see in Young's double-slit experiment. That's a classic example of light interference. To see that happen, though, we need two sources that emit light waves in a consistent, well, in sync kind of way.
So like their peaks and troughs are always lined up.
Exactly. They have what we call a constant phase relationship. Think of it like two dancers moving in perfect synchronization. That synchronized movement or constant phase relationship is key to seeing those interference patterns.
Okay, I get it. So you need two light sources that are perfectly in sync. But why don't we see interference patterns everywhere? I mean, light is hitting stuff all the time, right?
That's a great observation, and it leads us to another awesome phenomenon. Diffraction. That's the tendency of waves to spread out as they pass through an opening or around an obstacle.
Diffraction. Is that why you can sometimes hear someone talking, even if they're behind a wall? Like the sound waves bend around the corner?
Precisely. Diffraction is like this fundamental characteristic of waves. And light, as we've been discussing, is a wave. The reason we don't usually see crazy interference patterns is because, well, the effects of diffraction are often too small for us to notice with visible light.
So you need really, really small openings to see diffraction in action.
You got it. In Young's experiment, light goes through two tiny slits, which creates two sources of light waves that are, well, coherent. As those waves spread out from the slits, they overlap and interfere. Where the peaks line up, you get a bright band. Where a peak meets a trough, they cancel each other out, and you get a dark band.
That pattern of bright and dark bands, that's actual proof that light acts like a wave. What if you only use one slit, though?
Great question. When light goes through just one narrow slit, you get a different kind of diffraction pattern. Instead of those equally spaced bright fringes like you see with two slits, you get a central bright band that's much wider and brighter than the others, and they kind of fade out as you move away from the center.
So the single slit pattern is more spread out and less defined than the double slit pattern. Is that why, like, shadows don't have terrifically sharp edges?
Exactly. Diffraction is why shadows are a bit blurry around the edges. Light bends around the edges of the object, which softens the boundaries of the shadow. It's also why there's a limit to how much detail we can see, even with powerful microscopes.
Wait, really? Even with the best technology, there are things we just can't see clearly because of the way light behaves.
That's right. Light waves spread out as they pass through lenses, which puts this fundamental limit on how close two objects can be and still be seen as separate things.
Huh. So diffraction is both a limitation and a source of beauty. Isn't it what causes the colors we see on a CD?
Absolutely. Those closely spaced tracks on a CD act like a diffraction grating, splitting white light into all those colors. That's how you get that rainbow effect. And it's the same principle that gives soap bubbles their shimmering, iridescent colors. The varying thickness of the soap film causes light waves to interfere in a way that makes certain colors brighter.
So diffraction is behind rainbows on CDs and soap bubbles. Pretty amazing. It's incredible how one principle can explain so much.
It really is. And speaking of cool things about light waves, there's one more thing to explore.
Polarization.
Polarization? I think I've heard that word before, but I'm not really sure what it means.
Remember how we talked about light waves vibrating? Well, polarization is all about the direction of that vibration. Most light sources give off unpolarized light, meaning the electric field is vibrating in all sorts of random directions. But we can filter that light, so we only get waves vibrating in a particular direction.
So it's like taking this jumbled mess of vibrations and making them all move in a more organized way.
That's a great way to put it. We use something called polarizing filters, or Polaroids. Imagine them like a tiny picket fence that only allows light waves vibrating in a certain direction to pass through.
So a Polaroid is like a gatekeeper for light waves. What happens to the light waves that aren't vibrating in the right direction? They get absorbed by the filter. Think of it like trying to thread a needle with a thick rope. Only the part of the rope lined up with the eye of the needle gets through.
That's a good analogy. So the light that comes out of a Polaroid is polarized because its electric field is now vibrating in just one direction.
Exactly. And this polarized light has some really cool properties. For example, if you shine polarized light through a second Polaroid that's rotated 90 degrees from the first one, no light gets through.
Really, the light just vanishes.
Well, it doesn't disappear completely, it just gets blocked by the second Polaroid.
Ah, okay. So it's kind of like a light switch, but you control it by rotating the filter. That's pretty neat.
It is. And the amount of light that gets through the second Polaroid depends on the angle between the two filters. There's actually a law that describes this called Mathis's law.
So if the filters are lined up, all the light goes through.
Yeah.
And if they're perpendicular, none of it does. And, in between, you get different amounts of light depending on the angle.
Exactly. And this is used in a bunch of different applications, from sunglasses to LCD screens and even 3D movie glasses.
Wow. Polarization isn't just some physics concept. It's actually being used in things we use every day.
Absolutely. Like, polarized sunglasses work by blocking glare, which is basically sunlight that's been reflected and polarized horizontally.
And LCD screens use liquid crystals and polarizers to control which parts of the screen light up to create the images we see.
Precisely. And those 3D glasses, they use polarizers to send different images to each eye, and that's what creates the illusion of depth.
It's amazing how something as simple as the direction of light wave vibrations can have so many applications.
It really is. And it all goes back to Huygens' idea that light acts like a wave. Who knew such a seemingly simple idea could unlock so many secrets about the universe?
This has been an incredible journey through the world of wave optics.
Yeah.
I feel like I'm seeing the world in a whole new light, literally.
Haha, I love that. It really is a journey. But our understanding of light, even with Huygens' wave theory, isn't quite the whole picture.
Wait, there's more. I thought we had it all figured out. Light is a wave. End of story.
Well, it turns out that as physicists started exploring the quantum realm, they found something really surprising. Light can actually behave like a particle too, especially when it's interacting with matter.
Hold on. Are you saying light is both a wave and a particle? How's that even possible?
Yeah, it's one of those things that's really puzzled physicists for over a century. Quantum mechanics, it can be kind of weird. It challenges the way we normally think about things. This dual nature of light, we call it wave-particle duality, has really changed how we see the universe.
Okay, my brain is officially melting. So
Yeah.
light is a wave spreading out like ripples, but it can also be a particle, like a tiny little packet of energy.
Exactly. It's pretty wild, right? And here's the crazy part. Which aspect of light we see depends on the experiment we're doing. Like in Young's double-slit experiment, light clearly acts like a wave. You see the interference, the diffraction, but in other experiments, like the photoelectric effect, light acts like a stream of particles, those photons we talked about.
So does light switch back and forth? Wave, particle, or is there something else going on?
That's a question that has caused a lot of debate among physicists. Right now, the way we understand it is that light has both wave and particle aspects all the time. It's not like it's flipping back and forth, but rather it exists in this weird quantum state that honestly doesn't really make sense to our everyday way of thinking.
I'm starting to see why physicists might argue about this. So light is more complicated than we thought, but if light can be both wave and particle, what about other things in the universe? Do they have this duality too?
Now you're getting it. This wave-particle duality isn't just about light. It turns out that electrons, protons, even atoms themselves can exhibit wave-like behavior. It's this fundamental principle of quantum mechanics that's really changed how we understand matter and energy at their most basic levels.
Wow, so you're saying everything around us, even us, could be thought of as both a wave and a particle at the same time.
Yep, that's how we understand it now. Pretty mind-blowing, right?
It is. But maybe let's step away from the quantum stuff for a bit. I was thinking back to what we were talking about earlier. You mentioned that Huygens' principle can also explain something called total internal reflection.
Oh, yeah, that's a really cool phenomenon, and it's actually super important in technology like fiber optics, how we send information at the speed of light through these incredibly thin glass fibers.
I've always wondered how that works. What does total internal reflection have to do with it? And how does Huygens' principle explain it?
Okay, so picture this. You have a ray of light going from, say, water into air. Water's denser than air, right? So when that light ray hits the surface, it bends away from what we call the normal line.
Right, right. It bends because the light speeds up in the air.
That's it. Now, as you increase the angle at which the light hits the surface, we call that the angle of incidence, the angle of refraction. That's how much it bends, also increases.
So it bends even further away from that normal line.
Yep. Now, imagine you keep increasing the angle of incidence. Eventually, you hit this special angle called the critical angle. And at this angle, something really interesting happens. The angle of refraction becomes 90 degrees, so the light ray is basically skimming along the surface.
Like it's just gliding along the edge.
Exactly. Now here's the kicker. If you increase the angle of incidence even more, past that critical angle, well, refraction just stops happening altogether. Instead, all the light gets reflected back into the water. That's total internal reflection.
It's like the light hits an invisible wall and bounces right back. It could hit a mirror or something.
A perfect analogy. Now, here's where Huygens' principle comes in. Remember those secondary wavelets? Well, when that angle of incidence is greater than the critical angle, those wavelets created at the surface can't spread out into the air anymore. They're basically trapped in the water. And they combine to create a reflected wavefront, which is what causes that total internal reflection.
It's pretty neat. It's like the light ray gets to the boundary and it's like, nope, can't go that way. Got to turn around.
Haha, yeah. And this is exactly how fiber optics work. The way those glass fibers are designed, the light rays always hit the inside surface at angles greater than the critical angle, so they just keep bouncing back and forth inside the fiber, traveling long distances without losing much energy.
So the light's constantly zigzagging inside the fiber.
Precisely. And because light travels so fast, fiber optics let us send tons of information over huge distances with very little signal loss.
Amazing. I never knew something as, well, simple as total internal reflection could be so important.
It just goes to show how powerful it is to really understand these fundamental ideas about how light behaves. And it all builds on the work of those brilliant minds like Huygens and Young and Fresnel, who were willing to challenge what people thought they knew and, explore the universe with open minds. Their work has led to so many technological advances, and it's helped us understand light and the universe so much better.
It's really inspiring to see how far we've come in understanding light, and to think about how much more there is to learn. What other secrets is the universe hiding from us, I wonder? It makes you wonder what we'll discover next, right? Maybe someday you'll be the one making some big breakthrough about light.
You never know. But for now, it's pretty cool to just sit back and appreciate everything we've learned in this deep dive. We've gone from, basic wave ideas to understanding how those same ideas explain how we see the world around us. Rainbows, 3D movies, it all comes down to light being a wave.
I gotta admit, I'm feeling a bit overwhelmed by all this information, but it's a good overwhelm. It's just amazing how much we could learn from, just a few pages of a textbook.
And we're just scratching the surface. This deep dive, it's giving you a starting point to explore even more complex things, like holography and quantum optics. There's a whole world of knowledge out there just waiting to be explored.
I'm definitely inspired to keep learning. But before we wrap up this incredible deep dive, what about that thought-provoking question you mentioned? Something to really make me think about the mysteries of light.
Okay, here's something to ponder. If light, which we think of as a wave, can also act like a particle, which is what modern physics tells us, what other things in the universe might have these hidden dualities? What if what we think we know is just a tiny part in a much bigger, more interconnected picture?
Whoa, that's a real head-scratcher. It makes you wonder if everything we thought we knew was wrong.
Right. But that's what's so great about science. It's this constant process of asking questions, exploring, discovering. It encourages us to challenge our assumptions and be open to the unknown.
Well, I'm feeling pretty motivated to stay curious and keep exploring the universe and all its wonders. Thanks for being such an awesome guide on this deep dive. I can't wait to see what other cool topics we uncover together.
Always happy to explore with you. Keep those curious minds engaged. And until next time, keep on learning.